So what we're doing here is that we're now looking at method 2. Remember what I said, Cramer's method is the method of choice. This is the one you want. The other one really sucks in certain situations, really bad. And so we're defining differentials and integrals as operators. And what happens when you do that is that you now get algebraic expressions. And so all I'm doing is that I'm doing a very, very simple, operator exchange. So you can see that the differential with respect to time is just s hat. The inverse of that, of course, should be s hat inverse, the integral. Then the capacitor inductor equations now have a different viewpoint. They look exactly the same, but they're just in operators. So the process for deriving the second order equation follows the exact same process. The only thing that's different is step 4. So when you go to step 1.4, we're now going to use operator matrix calculations instead. And so you do step 1, 2, and 3 exactly the same, except now you put operators instead. But then what you find here is that in step 1.4 is you get a 2x2 matrix. And we don't want to do anything that they teach you in math, like the row reduction or the Gaussian method, whatever you want to call it. That's not very time efficient, if I could say that. This is way more time efficient, where you take the determinants of these guys, and I'll come in and I'll show you how to do the calculation. And what we're interested in here is we're not so much interested in like doing a ratio of matrices as you may, if you understood what you were doing with the matrix calculations. One way of doing it, at least with Cramer's method, is that you get a division between two determinants. And this one here, you're going to see that we're not going to really do that. And I'm going to isolate it so I have one determinant on the left side, the operators, and then the right-hand side is going to tell us about the cofactors or the effective sources in the circuit here. So what I'm going to do here is that since this is really the only big different step here, is I'm going to go in and I'm going to do a sample example. Then we'll do the example that's listed in, that I wanted to do here. Okay, so let's go do this. So here I go. So what I'm going to do now is that I want to do another example circuit. So note, I'm doing 4 examples of just deriving the differential equation. And I already told you, you gotta be able to derive the right equation. Otherwise, you're solving a different circuit. I mean, I guess that's nice, but it's not going to help you on the exam or quiz. You gotta get this equation right. And I'm expecting to derive it probably another 3 or 4 times before the end of the chapter. Super, super important. So what are we trying to do here? Here's my simple circuit. I have a source, and I have this guy right here. A nice simple circuit. And what I'm doing here is that I'm essentially trying to make the numbers as nice as possible so that we could keep them in. So what do I want to do? I want to determine the equation for IL. Okay, I want that second order equation for this guy right here. Here we go. So remember, I'm going to start to do things in a little bit more concise method here. So what I'm going to do here is that I'm going to try to do step 1, 2, and 3 simultaneously. Okay, so I'm going to do step 1.1, 1.2, 1.3, all simultaneously. So what's the first step? defined x1 and x2. In the operator method, it's not as crucial as it is in the substitution method. Because in the end, we're going to have a matrix that we then decide which operator we want to solve for. So, but I'm going to keep defining things. So I'm going to say, I'm going to define x1 as VC and x2 as IL. Remember this. This tells us which one we're going to do. Now what I'm going to do here is that I have to connect the currents and I have to connect the voltages. Okay, so let's do that. So the first thing I'm going to do here is that I'm going to look at KCL and I have to relate what? I have to relate IL and IC. So look at the circuit. What do I see here? I have a current coming in. Then I have 3 currents going down. So KCL at this top node tells me that I'm going to get what? I'm going to get the current of the 1 ohm resistor, the current of the inductor, the current of the cap. So right away, what I got to do here is that this tells me here is that KCL at the top node tells me that I of the 1 ohm plus I of L plus I of C equals I of source. Okay. Now, we can see that all of these guys have the same voltage. So if I come in here, you can look at these guys and you could just say, okay, here's my ground. And then I got to define what do I want to call the top node? I could call it VC. I could call it VL. And what I'm going to call it in this case, I think I'm going to call it VL. Well, what's easier? I think I'm going to call that node. It really doesn't matter because they're all the same. So I'm going to say that I'm going to call my top node. I could call it VL or I could call it VC because they all have the same voltage. So look what this does now. So the next thing that you want to think about is look at that 1 ohm resistor. That 1 ohm resistor has to be written in terms of one of the 4 variables, VC, IL, VL, or IC. So what I'm going to do here is that because I have these all in parallel, this has to be 1 times VC. So it's VC. So if I then equate this, this then tells me that I'm going to get VC plus IL plus IC equals I source. Check it out. I have everything in terms of one of the 4 variables, VC, IL, IC, but in this case, there's no VL. Now I'm going to go to KVL. KVL then says relate VL and VC. Well, since everything's in parallel, look what I'm going to do. I'm going to, of course, then VC must be the same as VL. So we're done, right? So if I bring this guy all the way over here, I'm not doing anything different, but all I'm doing now is that I'm really doing this to the other side here. So you could see I've now applied KCL, I've now applied KVL. And when you look at this, this has 2 equations, 4 unknowns. I got to reduce that. So what's the next step? Step 3 is that now I convert VL and IC into IL and VC. So here I come. So then the next step here is to then go in and write VL. Look at the inductor is 1. So then this is 1 times S hat IL. And if I look at IC, you could see that C here is 1/2. So I'm going to write 1/2 S hat VC. So I've now converted VL and IC in terms of VC and IL. So if I do that, let's keep writing it. So if I keep writing it, I could see here that I'm going to get VC, IL, look at IC. So then this becomes 1 half S hat VC equals IS. I look at my second equation. This guy reads VC minus S hat IL equals to 0. Check it out. I now have two equations, two unknowns. So in this case, I mean, if we look, we're solving for IL. So this guy becomes equation 2, and this becomes equation 1. And so what we want to do next here is that if we were looking at our boundary conditions or initial conditions, that would be equation 2. It's not so important in the matrix method. So now here's what you get here. You get step 1.4. So now what we want to do is that we want to derive second order equation using Cramer's rule. So let's go do this now. And so what we're going to do here is that now I need to collect all the VC and the IL terms. So let's look at the first equation. So if I look at equation 1, look what happens. You could see that I have two terms. Let's combine them. So this is going to be 1 plus 1 half S hat, and this will be VC. And then I have a term IL equals to IS. Look at my second term. This is VC minus S hat IL equals 0. So now if I put this into matrix form now, so I'm going to collect my VC terms. So my VC terms should look like 1 plus 1 half S hat, 1, and then this guy's going to be 1, and this is minus S hat, and you could see I now have a matrix that looks like this. Okay, and so what you find here is that when you look at this thing here, this is an operator matrix. It's not in terms of numbers, it's in terms of operators. And so what you do here is that we now go in and we apply Cramer's rule. So Cramer's rule essentially says the following thing. Okay. So if we come back up here, let me see if I can go get that. I just want to see if I have it. I don't think, for some reason, I'm not seeing this. Oh, never mind. I'll just show it to you. By the way, I should have written that this was equation 2, just to be, the way Cramer's rule works is it does like this. Imagine, so Cramer's rule says the following thing. Imagine that you have a matrix, and this guy is going to be looks like this. So the way you solve for the variable x is that you take this cofactor matrix. So a lot of times they call this the cofactor matrix. And since, look at the C's are related to this column right here. So the X terms are related to A1 1 and A1, 2. So I then replace the C's with the A1s and A1, 2. So then I come in here and it says, I want the determinant of C1, C2, A21, A22. And then it's the determinant of the cofactors. And then check it out. If I want the Y solution, then I replace the C's with the A211, A21, and A22. So then I come in here and I keep this the same. And then I replace this with C1, C2. And then I take the exact same determinant of the cofactors. Now, what's special about this technique is that in this situation, this guy D, which I'm going to define here and here, this is an operator matrix. So what you do here is that you typically would then rewrite this and arrange it as this. So then you come in here and you go, this is D hat times X, which is then equal to C1, C2, A21, A22. So if I look at this thing, it goes like this, where D hat is the determinant of this guy. And you can write this with the Levi-Civita symbol, or you could just think about this as a cross product. So you go in this, ooh, that's too thick. So you go in this direction. You go like this, that gives you a plus sign. And if you go in the opposite direction, you get a minus sign. So in other words, it goes like this. It's A11 times A22 minus A21 times A12. So then if you sort of look at this whole solution, the whole solution then is going to look like this here. So I get A11, A22 minus A21, A12 operating on X, and then I do the exact same thing. I take the determinant of this guy. So then again, I do the same process. That direction gives me a positive, so I get positive C1 times A22. And then when I go in the opposite direction, I get a minus sign, which then gives me A21 times C2. And that would be the solution for X. By the way, I can do the same thing for Y. So if I look at Y, look at the determinant D hat is the exact same thing for Y as it is for X. So then the Y solution reads then, you're going to get D hat Y. I won't write this guy out because we already wrote this, but then look at the determinant. I get A11, A12, C1, C2, and then I do the same process. That gives me a positive, so I get a positive, A11 times C2, and then I get a minus when I go the opposite direction, and then this becomes C1 times A12, and that would be the solution. So now what we want to do is that we want to apply it to this equation right here. So let's now apply Cramer's rule to this guy right here. So here I am. So what I'm going to do here is that now you could see that this guy right here is my D hat. Okay, that's my D hat right there. So here I go. So now what I do is I have a choice on which equation I want to solve. I have a choice. we decided that we were going to solve for IL. But I have a choice right now to solve for VC if I want. I can decide that at the end.
Carlos,
That's
can you leave it scrolled
not
up?
necessarily true for the direct method. Once you pick that direct method, you're already setting up your equations. Was there a question?
Can you leave it scrolled up a touch higher?
I'm not really hearing.
Scroll up.
Could you leave it scrolled up a little bit higher?
Sure.
Thanks.
Okay, so then check this out. Look what I'm going to do. So right now, I'm going to do this twice so that you can see. I'm going to solve for IL. So look what I'm going to do. So the first thing what I do is that I take the determinant on the left. Okay. So if I take the determinant on the left, then that means, look what I'm doing. I'm going this way. So I'm going to get plus. And when I do plus, look what I'm going to get. I have a minus here. So I have minus s hat operating on 1 plus 1/2 s hat. And then I got to go the opposite direction. So when I go the opposite direction, I'm going to get my minus sign. And then I'm going to get 1 times 1. And this whole thing, I'm going to say, is operating on L right now. So this whole term right here is my d hat. So if I clean this up a little bit, okay, well, maybe I shouldn't clean up. Maybe I should go to the right here. Now, look what I'm doing here. I have my cofactor matrix that I got to take the determinant of. Look at IL. IL is the second term. So therefore, I take my constants on the right and I substitute it into the matrix in the second column. So I mean, I have 1 plus 1/2 s hat, 1, right? That's the first one. But this guy here is the second column. So that means I got to focus on this column right there. So here I go. I'm going to replace this guy that looks like this. IS and 0 right there. So now I start my process here, right? And then I go like this. And what you're seeing here is that the first term is 0. The second term is going to be minus I source. So let's go write this down now. So if I clean this up, look what I get here. I get minus s hat times 1 minus 1/2 s hat squared. And then I get minus 1. And all of this is operating on IL. And then on the other side, you could see that the first term is multiplied by 0. The second term is going to give me minus I source. And you could see that I have all these minus signs that cancel out. So that now the second order equation reads, check this, I get rid of all the minus signs. So I'm going to get 1/2. So look at that 1/2. I'm going to multiply everything by 2 to get rid of the 1/2. So then I'm going to get s hat squared. Remember, I'm multiplying everything by 2. So then this gives me 2s hat plus 2. Everything's operating on IL. And then this will give me 2 I source. That's my second order equation. So now, if you insist on putting it into differential equations, then here I go. I know that the s hat operator is what? The second derivative with respect to time plus 2, the first derivative, plus 2, all operating on IL. So therefore, that's my second order differential equation right there. Okay.
Yeah, heel pace.
Say that again.
This is good. This is good.
Right on. Okay, so let's move on.
Hey, Carlos.
Yo,
So obviously this method is way better. When would we, is there any case when we would have to use the direct substitution instead of this one?
oh hell no.
Oh, nice.
Oh man. God, it just this is just so much cleaner. So much cleaner than the direct method. So there's my differential equation. So now let's go check it. If I want to go check it, what do I know? So what I do know is I knew this here. So then I'm going to go to check to see if this is true. So then I'm going to go to step 1.5. And this guy, what it does here is that you're going to check the equation and you want to determine the force response. IL of infinity, which I call B. So here I go. So I know that IL at infinity has to be a constant. So then this tells me that clearly if I have s hat squared operating on B plus 2 s hat operating on B plus 2B, that this term, if I take the derivative of a constant, of course it's 0. So then this tells me that then the inductor here tells me this. This tells me then that IL of infinity, which is B, must be the same as the source current. So this is what this equation is telling us. Let's go back to the circuit. So now we go back to the circuit, and the circuit looks like this. I have I source, and I have a resistor, but the inductor now is a short. So we know for a fact that this is at infinity here. And then the cap does what? It becomes an open. So, and you can see here is that that short's going to kill everything off. So that tells us here is that IL at infinity is the same as I source. So check this out. That equation then tells us that it's looking pretty good. Okay. So let me go to the next example here. Oh man, where did I put those examples at? You know what? Give me a moment.
I have a question.
Yeah.
So I was noticing Cramer's method looks really similar to the variation of parameter method for solving differential equations. Is it related to that at all?
I'm sure it is. I'm absolutely sure it is.
Yeah, because I just that determinant over a determinant times a derivative that's a solution is exactly the same as a variation of parameters method.
Yeah, I agree with you.
Okay.
And so I'm 100%. But this guy has the label of Cramer's rule, and that's the only reason why I use that. That's
Got it.
the more common way that people actually write this down. So, man. So I'm going to tell you right now, my internet has been very unstable since yesterday. So if I go out, note that it's not on purpose. And I'll come back. But in office hours today, I got knocked out a couple of times. So I'm hoping that doesn't happen. Okay, so let's go do this example now. Okay, so here we go. So ultimately, what I'm looking at is I have this circuit, and we want to use this to determine the differential equation for VC. And again, there's assuming that the source turns on at assuming Vs is really U of t, then that implies that at t equal to 0 minus, Vc of 0 minus should be 0 volts. So therefore Vc of 0 plus should be 0 volts. You're going to see that it's going to get more complicated because you're going to see that you'll have multiple sources in the circuit. And so Vc of 0 plus is not 0. But for right now, I'm just setting that up. And what we want to do here is that I want to look at Vc at infinity. And what we find here is that you could see that at Vc at infinity, what am I actually seeing here? What I'm seeing here is that I'm seeing that as the cap goes open, this 2 ohm resistor goes dead. And as it goes dead, what we're finding here, so I'm not really sure what happened here. What you're finding here is that the inductor goes to a short, so that cap at V equals to infinity has to be 0, right? Has to be 0. So what we want to do here is that we want to go in and we essentially want to get that and show that that equation must be true. Okay, let's go derive it now. So we know that this guy has to be 0. So our solution better show that that's 0. Let's go do it. So for us to do it here, we then start our process here. So what am I going to do? I'm going to try to do all 3 methods simultaneously. Okay, so here I go. Step 1.1, 1.2, 1.3. Okay. So the first thing that I'm going to do here is mostly for the initial conditions that we're going to need. So we're solving for Vc, of course, as it says. So now what I'm going to do here is I'm going to set x1 equal to IL, x2 equal to Vc. And again, this is really for like step 3. And we're just still on step 1. So now I start my process. I need KCL, I need KVL. What do I got to do? I got to relate IC, IL, and I have to relate VC, VL. Let's do that. So what I'll do here is that I'll define some nodes. Okay, that's one node right here. I'll look at this node right here, and then I'll set this other node right here. And of course, we have our ground, right? So when I look at this node, you could see that a good name for this guy, of course, is VS. A good name for this guy, of course, is VL. And then that guy must be VC right there. So let's start looking at this. Let's look at the current. So I need the current of the inductor has to be related to the current of the cap here. So when I'm looking at this thing here, what am I seeing here? Well, I can see right away that this guy has to be the current of the inductor. And because the 2 and the cap are in series, that guy has to be the current of the cap like that. But if I look at the current in the source branch, you could see that this is the current of the 1 ohm resistor. So then KCL at the inductor node tells me this. Tells me that I, 1 ohm, has to equal the current of the cap, of the current of the inductor and the cap. Wait a minute, I see that 1 ohm resistor. So I got to rewrite this thing in terms of the inductor or the cap. So look what I'm going to do. I can see that the node voltages across the 1 ohm is Vs minus VL. So that's what I'm going to write. So then I'm going to rewrite the resistor. So I'm going to write this as what? Vs minus VL. Of course, that's all over 1. but typically I ignore that one. And then this guy has to be IL plus IC. So if I rewrite this thing and I clean it up just a little bit, you could see that this is going to be IC, IL, VL equals V source. Here I go. Look at that. I have one equation with three unknowns. Let's go to the voltage here. So if I go to the voltage, I can see that the voltage of the inductor must be equal to the voltage of the 2 ohm and the cap. And I can do this with a little loop if you wanted to, right? So I'm focusing on that right loop. So if I do that, what do I see here? Well, I see that VL has to equal V2 ohm plus VC. Look at the resistor. I'm focusing on this resistor, and I got to change that resistor into one of those four variables. So then here I go. I see that this guy, look at the node voltage. I could either define that voltage as VL minus VC, or it's easier in my mind to rewrite this as that since it's in series with the resistor and the cap, then they must have the same current. So I would rather write this as the voltage 2 times IC. So here I go. So then I write VL and I replace this by 2IC plus VC. And then if I clean this up, you could see that then this guy's going to read VC plus 2IC minus VL equals to 0. And here I'm at the stage now. This gives me two equations, four unknowns. So you always got to get to that stage. So now what I got to do here is that I got to rewrite this in the language of the capacitor and inductor equations. So now I got to reduce those four unknowns down to two. So what I'm going to do here is that I'm going to copy these guys and I'm going to bring them down here just because I've run out of space. So if I paste these guys right here, now what I got to do here is that what I'm going to do now, right, I need to reduce these to two unknowns and two equations. And how do I do that? Well, look at IC. IC is going to be what? The cap value. What's the cap value? Here, let's keep bringing the circuit with us. So if I keep bringing the circuit with us, it's going to look like this guy. Look at the cap. The cap is 1/2. So that means I got to replace this with 1/2 S hat VC. Look at VL. The inductor's 1, so this guy has to be S hat IL. So I replace them. So then I just keep going along this direction. So look at IC. I'm going to collect IC terms, or VC terms. So this is going to be 1/2 S hat VC. And then I'm going to get IL. And then VL is going to be plus S hat IL, and that's going to be V source. Again, I got two terms to replace. I got VC plus, look at that, 1/2 times 2 is going to give me S hat VC minus S hat IL. And this guy's going to be 0. Here are my two equations, two unknowns. So now you could see that they're in matrix forms. So now let's go apply step. So now I want to apply step 1.4, which is Cramer's rule.
Carlos,
Yes.
if you were to say it explicitly, how do you choose which terms to sub for?
You're talking about, I mean, I'm really thinking as an algebra equation, right? I have four unknowns. I want to get it down to two unknowns that are going to be in terms of IL and VC. So I have to substitute IC out, and I have to substitute VL out.
Okay.
And that's
cool. It's
and that's what I wrote right here. Is that the question you were asking?
Yep.
I didn't hear what you said.
Yeah, that answers my question.
Okay,
Thanks.
good. So now here I go. So look what I'm going to do. I'm going to collect my VC terms. I'm going to collect my IL terms. So on the left, you could see that I can write a matrix that reads 1/2 S hat. So let's be careful here. I think I want to do this a little bit different. Let's call this equation 1. Let's call that equation 2. Yeah, 1. And then I'll say this equation 2. So what I'm really doing is I'm collecting what? VC terms, IL terms, and then my constants. That's what I'm doing. So here I go. I'm going to go straight down the line. So the next term, you could see that's got to be 1 plus S hat. That's all my VC terms. Now I'm looking at my IL terms. My I get 1 plus what? S hat times IL. Then my next term is minus S hat. And then I get VC IL. And if I look at my right side, I could see V source equals to 0. Okay. What I want you to do here, but before we do this, and I should have done this before, if you were using the direct method, okay, if using direct method, which term is equation 2? And just as a reminder, equation 2 is the one that contains the derivative of VC. Can you see which equation has the derivative of VC? And equation 1 and 2 that I defined here? Do you see how there's both? It turns out that the direct method really sucks right now. It's not a problem for the operator method because you use the exact same technique to do this. By the way, this equation has mandatory 4 initial conditions that are required. You could get away with 3 if you're clever, but this requires, in general, all 4 conditions, which kind of sucks. And it really takes that, 2 equations, 2 initial conditions for a second order differential equation. Not in real circuits, baby. This is a very, very, very hard initial condition problem. So then check this out. What am I going to do? I'm going to solve for VC. So here I go. So now what I'm going to do here is that I want to solve for VC. So what am I going to do? I'm going to take the determinant of my cofactors. So remember, the way we do this is we take the determinant of cofactors, and then we take the determinant of the determinant with the substitution of the constant terms. So here I go. I got to take the determinant of my cofactors. So here what I'm going to do. I got to take my determinant and I got to focus on 1/2 S hat, 1 plus S hat, minus S hat, 1 plus S hat. So this is my determinant, and this is going to be for VC. If I look at my right side, look at the VC terms. The VC terms is the first column. So I take my constants and I replace it in that column. So this is VS 0, 1 plus S hat, minus S hat. And that's my determinants now. Now, here I go through my process. And as you saw my process, I won't do this again anymore. I'm going to cross. And as I cross, I get plus and minus signs. So the first term, right? So if I look at this thing, I'm going to look at my first term on my left here. So if I look at that, you could see here that this is going to be what? Minus s hat operating on 1/2 s hat. That's my first term. And then my second term is a minus. And then you could see here is that I switch. So if when I switch, you could see that this is going to be 1 plus s hat, but this is really squared. So I'll write 1 plus s hat like this. So that's my right side. My left side then reads, check this out. It looks like I'm multiplying VS on an operator. That's not the way it works. Operators act on functions. So I really have this right here. So I get a plus sign, and then I get minus S hat operating on V source. It's not the other way around. It's an operator equation. And then our second term, of course, is 0 because I'm multiplying that thing by 0. So here we go. Let's clean it up now. So now to clean it up, what I'm going to do here is that I got to get what? Let's see. So if I clean this guy up, you could see here is that I have a minus sign, and a minus sign on all three sides. So there's no minus signs in the problem at all. All of the minus signs cancel out. So here I go. So my first term, which I'm going to focus right here, let's calculate that term. So that term should give me s hat squared 2s hat plus 1. That's the first term. That's this guy. Now let's look at the second term. The second term is then going to read plus 1/2 s hat squared. There's my second term. And then this guy is now operating on VC. So if I clean this up, you could see that I can add the square terms, which will give me 3/2 s hat squared, 2 s hat plus 1, operating on VC. And then if I look at the left, this guy's going to be s hat operating on VS. There is my second order differential equation right there. Do I have to put it in differential form? Nope. That works good, just like that. But typically, we should clean it up. And the way we clean it up here, because we need to do that, is that we need to isolate the s hat squared term. So if I do this, then if I multiply everything by 2/3, then I'm going to get s hat squared 4/3 s hat plus 2/3 operating on VS, and then I'm going to get 2/3 operating on s hat V source. This is proper form. Okay, and this is what I call proper form. Okay, so now I got it on proper form. So let's go check this thing here. So if I go check this, let me see if I still have my circuit right here. Yep, there's my circuit. What we already said here is that previously we said that this equation guarantees us that at infinity, this was 0 because the inductor shorts it out. Is my solution this way? So if V source is a constant, then that means that S hat VC must be 0. I said VC, I'm sorry, VS. Look at the right-hand side of the equation. I automatically have 0. So now what am I going to do? I'm going to take VC at infinity. I'm going to call that B. So if I put that into my matrix, my differential equation, this tells me then that I have S squared operating on B, 4/3 operating on B. And of course, since they're derivatives, these guys are all 0. And then finally, I get 2/3 times B. And then of course, the right side is 0. That tells us then that B is 0. And you could see that this guy and this guy match. So our first check on our differential equation looks good. Okay, so now we're done with that. So the next thing that we got to do here is that we got to go to step 2. So that's step 1. Let's go look at what process that we're looking at. So So if I look at my process, where am I at? I just did this. We've just completed step 1. Now there's a lot of algebra involved here. Now we got to go get step 2. Let's go look at that. So when we get to step 2, our goal here is we're now at step 2. And what we want to do here is that we want to determine the general response. We want to determine the general response. And so when I write the general response, what I'm really saying here is that I have x of t. I'm going to have the natural response plus the forced response. We know what the forced response is, right? This guy is known. What do I mean by that? Well, look, the forced response here was b for a constant source, is that we know that that thing's going to go to 0. So I know what the constant b is. But this is what we're going to find here. What we're going to find now is that I'm going to have 2 natural responses because it's a second order differential equation. I know what b is already. I will not know what A1 and A2 are. A1 and A2 have to come out of step 3. Okay? And so what we want to do now is we want the functional form of the natural response. So when we're doing this step here, our goal is to determine the functional form of the natural responses. And it really comes down to now solving a second order equation. In other words, we need to go in and we need to then focus on getting what those things look like. So let's go back and let's be careful here. So what we find here is that our second order equation will look like this here. So I'm going to get a second order differential equation. And then let's call this a1 dx dt plus a naught x. And then I'm going to have some type of forced response. And in this case, I'll just call it f. And remember, we already know that in our case, we're going to assume that that's a constant source. So the effective source is always a constant. So what we find here is that there's really 2 solutions to the differential equation. There's the f equal to 0 solution, right? And many of you will call this the homogeneous solution. And that really means that I have a differential equation of the natural response that looks like this. There's no source terms. If f is equal to a constant, as we're going to be doing, this here is our forced response. And I think you guys call it not the forced response, but I think you call it the particular solution, if I remember correctly. So in this case here, then I have a forced solution that looks like this here now. With this constant f right there. So that's what those solutions actually mean. I'm sure you already know that. So our goal here is that since we know what that force response is, our goal, of course, is to get the natural response. So here we go. So now what I want to do now is that I only will focus on the natural responses now. And what I want to do here is that in order to do that, we now got to interpret what the natural response of a two storage element circuits. So here we go. The natural response of two storage element element circuits. That's what our job is. And one of the key things is that you have to understand what are the characteristic equation and roots of the determinant here. So if I was to speak in the language of differential equations, when deriving the second order equation in operator form, you get this equation that reads d times x, and then you're going to get these cofactors, right? You're going to get a matrix of, with those constants here. Now this d is super, super important. This d, what it does here is that this tells us about the natural response. This matrix here, this tells us about the force response. We're interested in the natural response. So that's what we're going to do here, is that we need to go in. God, I got to find my mouse someplace. So here we go. So I want to focus on that. And so what you're going to see here is that I'm going to start off with an analogy first. And the analogy is that a damped harmonic oscillator has the exact same characteristics as an RLC circuit. And what you find here is that it looks something like this here. So to make it easy, I'm going to start off with the undamped oscillator. So if I have an undamped oscillator, we could imagine the following scenario here. So you could imagine that I'm going to hang a mass spring system where this represents the equilibrium. So if I'm looking at this oscillator, if I displace this oscillator, we know that we can write a differential equation. And by the way, I should be really careful with this picture here, because what I'm going to do here is that I'm going to set the acceleration due to gravity to equal to 0. Okay, so I'm setting the acceleration due to gravity equal to 0, so therefore there's no force of gravity. I could have drawn this horizontally too, but then we'd have to deal with coupled oscillators, and I'd prefer not to do that. So then, here we go. So then, if I look at Newton's second law, it tells me that the net force acting on the system has to be minus kx, which then tells me it's mass times the acceleration, which then tells me that I get this thing here. Okay, so there is a forced response here. And so when you really look at this thing, look what this equation really looks like. So if I rewrite this equation, it now looks like this. And then I can rewrite this thing that looks something like this here. So this guy's going to be what? I'm going to bring the kx term. I divide the mass. So then what I end up getting here is that I get k over mx. And look what I get. I get 0. So the proper form here is that they typically write it like this. So if you look at what this equation tells you here, check this out. This guy is equal to 0. But wait a minute. If it's equal to 0, that's the homogeneous solution that's going to tell us about this thing. And what it's really telling us is that that you get the following thing here, is that the solution to this guy will then be some constant where now I have some oscillation, the angular frequency or the angular speed of the thing. And at most, you may actually have a phase constant, but not necessarily, I mean, depends on the system here, but there's some phase here. So if I look at this oscillation, what am I actually seeing? So if I plot this guy, and let's say that this is x of t, and of course this is t, then I get a pure oscillation that oscillates forever. Right? There's no damping at all. It's a perfect oscillator. And of course, it oscillates between its maximum amplitude, in this case A, and minus A. And then the period of the wave is connected to the frequency, which is connected to the natural frequency of this oscillator. What happens next is that if one introduces friction / damping, right? They're not the same, but you could have that. And in this scenario here, you could imagine that I have my oscillator, and what I'm going to do here is that this oscillator is now in a container. So you could imagine that I have a system that may be moving through a fluid. So if I'm thinking about this fluid, this oscillator now is going back and forth in this fluid. So what you're seeing here is that you have to include damping. And since it's water, that damping typically goes as V, not as V squared, because you have regular laminar flow. So damping implies that that you're moving through a fluid that is laminar. And this implies here is that this damping force is typically minus BV, not V squared, right? V squared is about turbulent flow. So then this guy really becomes the derivative of this term right here. So if I now look at N2L here, what it tells us here is that the net force in the system is not only a spring-like force, but I now introduce a new term for the damping. And when you look at this thing, you're going to find here that this, of course, has to equal the acceleration term. And then if I clean this up, if I rewrite this whole thing here, I can then isolate the acceleration term, and it now looks like this. And so I now have my solution to our second order equation. And if you look at this guy, what do you actually see here? Well, it's a little bit complicated. The only way you can actually look at this thing here is that you got to look at the characteristic equation. So a lot of times people like to write a general solution here. And so what they'll say here is that the general solution essentially says this, which is not really correct, but they'll say that the general solution, they'll come in here and they'll say that now this solution looks something like this. They'll have a constant, arbitrary constant A, and then you'll get a solution that looks like B over 2M, and then you get a cosine. And then they have a phase. So you got to be really careful with the solution because this is a second order differential equation. You need two arbitrary constants. The two arbitrary constants is this A right here and this phase. You don't have to write the phase this way. There's a way of writing it differently where you get A1 plus A2, and that mathematically is just much easier to deal with. But in this case, this is an easier interpretation of what's going on. But just to make sure, these two guys, so that I'm not snowing you, these are the two arbitrary constants. And so your initial conditions must solve A and the phase. But here's what you find here, is that the type of response of the oscillator depends on the ratio B over 2M. And what you find here is that if you have a large B over 2M value, then you get a solution that we call overdamp. And then if you have a small B over M value, you get something called underdamped. And I know you've seen this in your differential equations class, but then there's this elusive value. And what you find here is that I should say that you get a critical value. And when you get this critical value, you get something called critically damped. So if you're looking at this thing it looks something like this. So if I go and I plot this guy, what does this guy actually look like? Well, it looks something like this. The overdamped turns out to take the longest. So in other words, an overdamp would probably look something that takes a long time to actually come down to zero. So this would be the overdamped. And if you have an underdamped oscillator, then we know that this guy essentially is going to do what? It's going to oscillate until it eventually dies down. And of course, this red here would then be our underdamped. However, we have that critical damp. And what's special about this critical damp is that it actually goes to zero the fastest. And this guy would be the critical damp. And you'll find here is that if you have a damper on your door, you actually want it to be critically damped because it's the fastest way to close your door. So what happens here is that in an RC circuit, the exact same thing happens. Okay? The exact same thing happens. And what's special about it is that you get the following thing here. Here, let me set this up. Apparently, I did something wrong. I got to set this up on a website real quick. Damn. Okay. Apparently, I'm not doing very well. Here, give me a moment again.
So once you get your final equation, is this something you can just plug into Desmos as a quick way to see?
Well,
If
I'm not
it's-
sure what you mean by that.
Like could you just graph it quickly in Desmos to see which one of these it looks the most like?
Yeah, you can definitely graph it.
Yeah. Oh, the solution, you mean?
Yes.
Yeah.
Yeah.
I know there's mathematical ways to tell if it's overdamped, critically damped, or damped, but you could also just graph it. Yeah.
Yeah. What you'll find here is that, like, what we will do, of course, is that we will be looking at oscillators in the RLC range that we can actually just calculate here. So what I want to do here is that,
Isaac, I should add a note. It's not obvious to me how you would tell graphically which of these.
so the hardest, well, the two easy ones, of course, are the overdamped and the underdamped. Without any doubt, if you go into the lab, critical is really hard. So if you're doing this mathematically, then I would agree with you that you really got to just solve the equation. You got to get that D value. You got to get this operator. That's what's going to tell you whether you have over, under, or critically damped. So we only got 5 minutes, so let me see if I can just highlight this and then bring this up. So I'm spending time on this thing because you're going to have to do this with an electric circuit. Okay? You're going to have to do this. So here we go. RLC circuit oscillations. So the question is, why is it that an RLC behaves like an oscillator system? So for starters, you go like this here. The first thing that you do here is that for an LC circuit, clearly the resistance is zero because I didn't include R, what you're going to find here is that the cap and inductor will oscillate the energy back and forth forever. And what I can do here is that I can do the following thing here. So let me show you. So if I go and I share my screen with you, here is an oscillator. This is by the German guy, really awesome guy. You could see here that the resistance is set to 0. I have a capacitance and I have an inductor here. Don't look at the back, the bottom of this thing, because that's really talking about AC circuits here. But check this out. Look at the oscillation. So I have a charged capacitor right now. Oh, wait. I'm going to charge the capacitor because of this thing here. And then the switch is going to turn, and it's now going to have an inductor and a cap. So let's start it here. So what you're going to see here is that now look at the oscillation. It turns into electric and this. Now, if I slow this guy down, look what happens. Look at the E fields. Boom. There's my inductor. My inductor now has no energy stored. There's no current in the inductor. All of it is in the cap. Now, look what happens. Now I'm going to let the cap discharge. As the cap discharge, you increase the current in the circuit. The magnetic field is growing in strength, and therefore the magnetic energy, boom. Now all of the energy is in the inductor in the form of a magnetic field. So now what do? I'm going to let the magnetic field energy drain from this, go into the cap, and you can see that the process is going to repeat until boom. It is now reverse polarity, and then we can continue to look at this thing. So the oscillation between the electric field stored in the cap and the oscillation of the magnetic field stored in the inductor will oscillate forever. And that's why these two equations are exactly the same. So when we go and we look at the oscillator, what you're finding here is that what you're seeing here is that this is what I mean. They will do what? The cap and the inductor will oscillate energy back and forth forever if there's no resistance. So then for an RLC circuit, the resistive element what does it do? Well, we typically say that it dissipates energy. But what it really does here is that this dissipation of energy, it's really a form of damping. And that form of damping adds a derivative term that's single order in time. Damn, dudes, we're out of time. I got a big day in 4B, 4A today because we're doing modeling presentations. So I can't be late. Okay, homies. I'll see you guys on Friday. Otherwise, I see you on Monday. Okay, take care, man.
Hey, Carlos,
Yes, sir.
when you